Okay, it's about the time that I'm gonna go ahead and get started. It seems like no one has showed up. That's okay. I can go ahead and then do this session and record and then upload to the homepage. Okay. Oh, somebody's gonna join. Hi, Magnus. How are you?
Yeah, I'm fine.
Yeah,
Hello.
good. Yeah, I just started. Okay, you didn't miss
Okay.
anything. I just started. Okay.
All right. Thanks.
Okay. Let's see that who else is gonna join. Let me see. Okay. Okay. Anyhow, that I have already shared the screen that we can continue the same discussion we had on Monday. What we're gonna do, we're gonna have a look at this mainly that sampling distribution. Sampling distributions of Y bar. Sample mean. Y bar means sample mean. Sampling distribution of sample means. See? Oh, some right. Let's see what's the problem here. Let me see. Get connected. Connect. Okay. Sampling distribution of Y bar is called the sample mean. Oh, yeah, Benjamin, he's waiting. Let me see. Did he get connected? Oh, okay. Okay. Hi, Benjamin. How are you? That I just started. Okay. You didn't miss anything. I just started. Okay. Okay. Let's see that. Okay. So that let's get back to that what we had been talking about the Monday sampling distribution of Y bar. We can talk about this one in two ways. I mean, like in order to get this done, sampling distribution, to generate the sampling distribution, to construct the sampling distribution. See, I would say construction. See, construction of sampling distribution of Y bar. That's what we are planning. Oh, it is not working. Let me see. Disconnected for no reason. Mm, yeah, probably she's gonna. She's gonna. Hi, Kali. Good evening. That I just started. Okay, you didn't miss anything. Okay, so let's look at that. I'm just continuing the same discussion we had on Monday, and then we can move on to that our assignment and other stuff. Okay, let's see the construction of sampling distribution of Y bar. We can get this done in as an example. I'm gonna use in that fingers data. Okay, fingers data. Fingers data. Under this one, I can get this one. I don't know, this getting disconnected. Fingers data. Fingers data. So one first method, I'm gonna call this one bootstrapping. Okay, you're gonna heard this word for the first time. Bootstrapping. Bootstrapping. Okay. Bootstrapping means resampling. Okay. Bootstrap means resampling. Okay. In another way, see, resampling. If you're gonna resample something, that's called the bootstrapping. See? Bootstrapping. So we're gonna looking at the bootstrap sampling distribution. Bootstrap sampling distribution. That's the one that we are looking into. Bootstrap one. How do you get this one? Okay. So you can remember by looking at that the rolling a die or throwing a die, the die or dice, we discussed that one. That's a very particular example in which we can have a look at it, that your population, population distribution, sample distribution, as well as sampling distribution very clearly. But in fingers data, you have a data only. You can draw a histogram for that particular data, but you don't have any idea how your population look like. But by looking at the data, you can get a rough idea how would your population would be. Okay. So that's the kind of a discussion we are building up. See, not this one. Okay. Let's see. Okay, this one. Let's go to that thumbnails here. This one, see, by looking at this, see, no, this is a simulated thumb. Simulated thumb. Okay, that's simulated thumb. Yeah. So we had an idea. See, this is a histogram. This is based on your sample. See, you have a sample. You know how to draw the histogram. And then this sample that you go to the mean value, that mean is not enough. Then you're gonna take the so many means, and then with the means that you are trying to build up a sampling distribution. But if you go back and then rather than talking about sampling distribution, the sampling distribution and population distribution, in between those two, there's another one called the sample distribution. This is the sample distribution. This is the sample histogram. Can we get a rough idea about the population distribution? Yes, it look like this one. This look like a normal. See, if you're gonna increase the sample size, which is 157, if you keep increasing the size, like let's say 1,000 student will be included here, 10,000, million, then this systematically becomes like a kind of like a get a rough idea. These gaps will be filled in. See, gaps will be filled in, and it will kind of like approximately or roughly becomes like a normal distribution. There's nothing wrong with this one to assume that your population for this thumb length would be a normal distribution. There's nothing wrong with that one. You can assume like that. But when it comes to the roll in a die, you cannot do that one. You cannot say that your population distribution is normal. You cannot. We had that discussion broadly. It is uniform. See, it is uniform for sure. Roll in a die. See, roll in a die. See, it's uniform. Uniform for sure. It doesn't look like something with a hump. And we did this one for the population. We did this one for the sample. Sorry, after see, sample look like this one. But when you increase this one, there's no way this bar to go beyond a certain point, which is the 1/6. See, if you're going to go to the relative frequency, which is the frequency divided by the sample size. So see, it becomes like a, by looking at this one, can you get a rough idea about the population distribution? Yes, it looks like a uniform. On the other hand, you don't have to assume that one. You can get a clear cut that distribution very easily by increasing the sample size, and then see, we increase that one to 10 to the power 6 or 10 to the power 9. Then you get the uniform. But here we had a different discussion. Here thumb length, our histogram look like this one. Because of that, you can assume that population is normally distributed. Okay, that's the kind of a discussion we are trying to build up. That's why when it comes to the bootstrapping, we don't have to worry about that one. What we're gonna do, we go ahead and utilize the same sample again and again and again. We're not gonna do that one physically, but the computer does that one for us. Okay, that's called the bootstrapping. Bootstrapping means you are wearing out, you are just using, recycling the same sample again and again and again. That's the same thing that we saw last time. So I would say, see, I would say this one. Can you remember? We can remember this one. We're gonna do this one 1,000 times. Okay. And we're gonna get the mean. Whose mean? Mean of the resample. Okay. Okay. Open. Go to the fingers. Go to the thumb. How many we need? 157. Okay. Close it, close it. Okay. What we're gonna do, whatever the sample that we have, we're gonna utilize again and again and again, and then we build up 1,000 samples. See, we're gonna build up 1,000 samples and then calculate the average for each and every sample. See, that's called the bootstrapping. This is bootstrapping. Whatever you have within hand, you have you're gonna bootstrap. This idea was put forward by Efren. Efren is considered to be the top statistician, the living legend in right now. I think he's with the Stanford, if I'm right here. So he came up with that idea. He's going to utilize, recycle the same one. Because of that, I would like to assign this one rather than calling a population or anything. I'm going to give you a new name for this one. Okay. B boot SDOM. What that means? See, that boot for bootstrapping. Bootstrap S for the sampling. D for distribution. Is simple of what means. Bootstrap sampling distribution. I'm going to call that one boot SDOM. Here, this is a frame. Once you do the do function, when you use the do function, you know that it is a data frame. What's the variable? This is the data frame. This is the variable. See? This is the variable. So for this particular variable, we're going to build up our histogram. See? It looks like that. Can you remember that we have, if you come to the pictorial form, can you remember? We had this one. From this one, you need a one sample. You need a sample one of let's say size n equals 157. See, 157. How do you get that one? You get that one, you go to the resample. See, that's the R code. In R, how do you get that one? Resample. You go to the fingers. You go to thumb and say 157. See, that's the R code. How to get that one? See, see. If you go to the second one, let's say that you have a second sample. See, sample 2. Sample 2 of size, same thing. Size n equals 157. What's the R code? Pretty much the same thing. It's been randomized. In that way, you're not going to pick the same thing. You have mixed them up. Resampling we are using because with replacement, okay? With replacement. Resample. Resampling means with replacement. And the second one, you can say resample. See? Go to fingers and go to thumb. Size of 157. You keep doing this how many times? Let's say 1,000 times. See? Sample. Can you remember I used to call this one m equals 1,000 of size n equals 157. See? But again, you use the same code. In R, you code the same code, resample. Fingers. So that's why you don't have to go to several times this one. That's why you use the do function. Okay. See? See? So this all will be done by what? Do function. See? One and do 1000 times the resample fingers from 157. See? All will be done by that one. See? Do function. Then what are you gonna do? You go to this one and you calculate y bar 1. See? Y bar 1. So what are you gonna do? You get the resample and then what? Then you can do the do over here that get this done. Y bar means that you're gonna find the mean of the mean of resample. See, that's in R. Resample fingers and thumb and 157. See, mean you find. That's y bar 1. See, if you want y bar 2, that's the same thing. Y bar 2. See, mean of resample fingers, go to thumb, size 157. That's the same thing we do over here. The mean, find the mean. If you need the y bar m, see, y bar m, if you need y bar m, mean, resample, fingers, $sign, thumb, sorry, thumb, comma, 157, 460. That's the whole thing we were writing like this way. Do 1000 mean, okay, resample, okay, fingers, thumb, 157 plus close. That's the same thing we call this one boot standard, the sampling distribution of n. See, that's the same thing. See, that's the pictorial. So once you generate that one, can we draw a histogram for that one? Can you draw a histogram? Yes, in R we can draw a histogram. GF histogram. I'm gonna do this one for mean. My data frame is nothing but boot sampling distribution of n. If you want, you can use a color. Let's say dark blue. See, you can draw histogram for that. See? So then, see, this is your this is your y bar. This is your count, or you can say frequency, which is f. See, once you draw this one, you're gonna have something like this. See? This is mean. You don't have y anymore. You have mean. See, if you since you are using the larger one, it's approximated by, according to central limit theorem, this mu, you can remember this mu, see? Mu of y bar is same as mu. It is same as what y bar, same as y bar obs. You can remember, we had this discussion. On the other hand, the spread is the center. The spread would be sigma y bar. See? Sigma sub y bar, if you want, you can call that. On this one, if you want, you can say mu sub y bar. Or you can say mu c sub y bar, or simply say mu y bar. See, doesn't matter. So this one is nothing but sigma over square root 10. It's nothing but see S over square root 157. S naught over 157. S naught means the S so where you can use that. See, that's how you get the bootstrap that histogram. See, it's a bootstrap histogram. It's a bootstrap histogram. You get the bootstrap samples. See, you get the bootstrap sample by just simply writing that. See. On the other hand, as I said earlier, for the bootstrap sample, you don't have to worry about the population shape. You don't have to worry about that one at all. Bootstrapping. You just utilize, recycle your sample again and again and again and again and build up whatever the sample. See, you built up samples. See, based on the existing sample, utilize in order to simulate samples. See, you generation of sample, construction of sampling distribution, or generation of data. See? And then find the mean, you do that one several times and then draw the histogram. See? Now draw the histogram and then you can see something and say that some kind of a question you can build up. You can say something like that. How likely we would randomly draw a sample of size n equals 157 with a mean higher than 61 millimeters. So this y bar is nothing but 60.1. 60.1. This this one is nothing but 8.73 over 157 square root, which is 0.697. 697. See, so the observed sample standard deviation is 8.73. Mean is 60.1. Now I have a question. I want to know that how likely we would randomly draw a sample or pick a sample of same size, 157, with a mean more than 61. More than 61. See, I need to answer this question. See, how likely we would randomly draw a sample of same size n equals 157, but the mean, oh, I'm sorry, draw a sample of size n equals 157, but with a mean, but mean would be how much? We don't know mean until we're gonna that calculate, no? Mean, I'm gonna say higher than, see? Higher than 61 millimeters. How do you answer something like that? See, how likely, how likelihood? Likelihood is nothing but, see, likelihood means probability. See, chance. What is the chance that we would randomly do a sample of size in 150 with a mean higher than 61 millimeters? Now you want to know that. When you pick a sample, you want to know that their average would be more than that one. When you pick a sample, you want to know that their cutoff value is more than a certain value, like that. That's kind of a discussion. This one is 61. Sorry, this one 61. 61. 61. We have sent a 60, but this one 61. That is, you're looking for what? You're looking for something like this. I would like this one, this one. Probability, P stands for probability. See? Probability that, okay, sample mean is greater than or equals to 61. See? Which is, I'm going to write in previous, y bar greater than or equals to 61. How much would that be? That proportion is how much? We really need that proportion. How do you get that? We can easily get that one with the aid of whatever the sample we have. Okay. With the aid of that. But before that one, to answer this question, I would like to go to the I can answer based on this histogram. It doesn't matter. Okay, same way that when I go to second method, you can use the second method and then do the same thing. But anyhow, let's say that if you really wanna, the two things you can do this one. You can calculate, you can show. See, this probability you can see. Graphically, you can show. See, graphically, numerically. You can calculate too numerically. See? Graphically calculate, as I told the last time, score, see, exploratory data analytics. This one, descriptive data analytics. See? How could you gonna graphically show that region? How could you gonna show that? You go to histogram, see, you go to histogram, histogram, okay, and you can remember you have a mean to that variable. Your data is nothing but boot sampling distribution of mean, and I'm gonna add something to this one. I'm gonna fill. I'm not gonna fill with the color. I'm gonna fill with that expression mean tilde mean greater than or equals to 61. That's the way how you can use show graphically. But numerical, how could you calculate this one? You're gonna go ahead and use the tally. Tally, whose tally? Mean greater than or equals to 61. Go to data. Data is nothing but boot sampling distribution of mean. See? That's how you're gonna do numerically. When numerically you do that one, okay, you have a result like this. Is the results, okay? Mean greater than or equals to 61. True. The other part is false. True mean, you know what do you mean by true? True means probability. Y bar greater than or equals to 61 region. False means probability. Y bar less than 61. You don't have to put if you want to put the equal sign in both, doesn't matter because these are continuous. No harm at all. But in discrete case, you have to be careful. Discrete case, if you put the equal sign to one number, that equal sign cannot be utilized for the other one, like in the 1, 2, 3, those numbers, but these are continuous thumb lengths. See, false. They give this number 0.105, the other one 0.895. 895. But if you add these two, they will add to what? All less to 1. The total probability is all less 1. So this is the result being displayed. Okay. So that means true part means that greater than part is 0.105. But on the graph, how it looks like on the graph. See? Let's say that I'm gonna one day. They will show that clearly. See this part, that part. Let's say this one is 61. Okay, more than 61. Okay, I'm gonna draw other side too. See, this is the probability. Y bar greater than or equals to 61, which is 0.105. 105. If I more clearly, if I draw that one more time on this side, And this is y bar. Let's say like that, okay, something like that. This is f equals, this is mu. So I'm gonna get the smooth curve scheme in the top of this one. I'm gonna go to the center. Center, you can remember always mu y bar, which is mu, which is observed based on the sample one. Sample one can be replaced by the observed one, which is 60.1. Okay, so the spread same way, spread sigma y bar, which is sigma over square root 10, which is s over square root 10, 157. S is 8.73 divided by 157.697. Okay, that's okay. But then we're gonna locate my value. See, my value is here, 60.61, 61, 61, 61. I'm looking for area under the curve. Area under the curve more than 61. See that region, shaded region. See, all shaded region. That area under the curve. See that area. I'm looking for the area under the curve, which is the probability. See, which is the probability. How likely that my sample would have like a mean more than sample of size 157 would have like a more than mean more than 61. See, that's the one we calculate 0.105. See, this side probability y bar less than 61 is nothing, 0.895. The total is what? All less 1. That's why we call them the probability distribution, not the mathematical distribution. See, we can get that one using R, both of them. You can get this region, shaded region. See, we have done that one a certain point. Keep going. Okay. They will show very clearly. Okay. They will show clearly. Okay. That's the idea. Okay. More than 61. That means how many students would have a thumb length? That's the idea. How many students as a percentage would have like a this one average more than 61? How many means means like how many means here actually in sample, how many means, sorry, not the how many student, how many average of the students would be more than 61. See? That's how they get that. So that's how you're gonna find that one. The similar in a similar fashion, the way that we did the sampling distribution, sorry, the bootstrapping, the second method I'm gonna call simulating. See, simulated sampling distribution. How do you simulate? As I said earlier, that I said that you can assume the population. See, assuming that the population distribution is normally distributed with a mean mu. Mu can be replaced by y bar, y car can be replaced by y bar obs. Y bar obs is 60.1. Can we do like that? Yes. It's mu 60.1. and a standard deviation, which is sigma. Sigma can be replaced by samples, standard deviation, sample standard deviation replaced by the observed value, which is 8.73. We generate samples of size n equals 157. I'm going to extract from the population samples. I'm going to assume that my sampling distribution is like this. Sorry, population distribution Y. See, thumb length like that. See, Y. Add a mean. See, mean 60.1. Spread sigma 8.73. I assume this is a population distribution. Okay. From that one, I'm going to extract. See, I'm going to extract the first sample 1 of size n equals 157. See, I need that one. And I calculate the y bar as like same way like last time, y bar 1. See, how do you do that one in R for this one? You're gonna go ahead and do this one. Normal, R norm. I'm gonna say R for random, okay? Norm means normal. R norm, see, R norm, how many? 157. Then you need the mean. How do you get the mean? Mean, thumb length mean. See, mean is nothing but 60.1. See, standard deviation 8.73. That's how you're gonna do it. See, R norm. R stand for random numbers. Norm means normal distribution. See, random numbers. See, R random numbers coming from the normal distribution. Norm means normal. See, normal distribution. See, normal distribution. Okay. R norm. So you can keep doing this one. Let's say the second one, sample 2 of size n equals 157. The same thing. R, see, in R language, if I'm gonna write this one, R norm 157 generate, and you have to supply its mean, which is 60.1, standard deviation 8.73. The second one, see, y bar 2. Then if you do this one, see, you can do figure y bar, see, 1002, see, 1000. You go to the sample m equals 1000 of size n equals 157. In R, you write the same R norm 157. You give the mean 60.1, standard deviation 8.73. So how do you create the mean? You know, you go to that one, R norm, and then you do that one. What? You're gonna find the mean. See, I'm gonna write for only one. See, mean of R norm 157, mean 60.1, comma, standard deviation 8.73, close. See, that's the same thing. I'm gonna write with the one line to that generate all at the same time. I'm gonna do this one 1000 times. Okay. I'm gonna generate the numbers and then find the mean. See, R norm 157 And the mean is what? Mean of that distribution is 60.1. And standard deviation is 8.73. How could we know these ones? This one, I'm going to call this one SIM, sampling distribution of M. See, I'm going to call this one SIM. See, SIM means simulated. Simulated sampling distribution of a simple O of mean. SIM SDO. Same way that you can draw the graph, everything you can do, okay? And then you can find the area to the right of, left of, anything. Doesn't matter. Once you simulate that one, you can draw the histogram. Same thing. See, you're going to draw the histogram for mean like that. Rather than see, if I write the general format, SIM SDOM, I'm going to write do 1000 here, 1000 done. But how did you get that this R known 157? I know the mean. How do you get the mean? I would say I'm gonna go to what? Thumbstat, and from Thumbstat I'm gonna go to the mean. See, and $sign mean, comma, and SD. Rather than we don't know, we don't have to get that number somewhere. Just give the code. He will do that work for us. We don't have to do the work. That's why we are using SD. Close it. Where? How do you get the thumbstat? First, you can get the thumbstat. That means 5-number summary. Favorite stats. Go to thumb and data coming from fingers. Okay, fingers. That's the original data set. From that one, you built up the 5-number summary. Those 5-number summaries, mean and standard deviation, utilized to get the random normal data. See, you extract data from that one, assuming that you know the population. You extract from the population. See, then you can easily draw the histogram for this guy too. See, EF histogram, mean, and data would be nothing but SIM sampling distribution of this one. And let's see, fill, you can say gray, black or the blue or something. Like that. And then you can do that same discussion over here too, the greater than, how likely that something would be like that. See, there are two ways, you have two types now, sampling distribution. Okay. Okay, those are the way that now you might be thinking why you are using the normal distribution. Can we use the other type of distribution? Can we go to this one? Sorry, go to this one, the uniform distribution. From the uniform distribution, can we generate the same way rather than doing this way? Can we do like that? Okay. Okay, see this one. Can we generate this one rather than do this way? Rather than doing this way. See? See? Can I generate, assuming that this is a uniform distribution line? Yes. You can use the R unif. Random numbers coming from uniform distribution will do that one. You can do that way too. Okay. Okay, let's look at our that homework and see that what we can build up over here. So you saw that see, so you have that simulated data, sim data set. Okay, those are simulated data set. You have 1,000 columns, and then you have 100 rows from the 100 students. Information being, see, remember that if you get a little bit information about this one. Okay. Assignment, number 2. It's in data. That's the data. This is the information. See, to download and import the simdata.cv file, which contains 1,000 samples. Each sample is a size of 100. See, sample of 100 students, or size 100, per sample. Each sample was taken each month for term at NU for the past 1,000 months or columns for a student currently enrolled in the class for that month. See? Itself is the age of a student for a term for histogram. So see, each sample, 100 students. Each month, they assume that this is like there's some hypothetical that example. This is something made up. Okay, so see, it's 1 next 2, see, like a variable. They look like the variable. See, the variable. Then you can find the average column wise or row wise, both ways. Okay, if you go to the sample average is this way. Okay, these are the samples. Okay, these are the students. See, that student being repeated through all these things. This way you can find that you average as well. Okay, let's see how to tackle this one. Okay, let's get this one. Okay, then this one, let's get the data. Let's go ahead and look at the dimension, dim. Okay, dimension, see, rows, number of rows, number of columns. First one, number of rows, see, rows, students, columns, samples. Okay, and the minimum value in the data set, I call that on data set 18. Maximum value, the age of that, the minimum age, maximum age 49. Number of columns, if you want number of column, n col. Number of rows separately if you want 100. Column means, if you want the column means, look at the column means. Okay, these are the column means. Okay, what this means, see, go to the first column, it's average. I'm talking about this one, column wise. Okay, I'm talking about this one, 33, all the way down to that this 100. The age is being added together and divided by 100. That value is the one that can appear over here. Okay, sum. Okay. In Excel you can do with the sum. So sorry, the average you can do this as the same thing. See, column 1. Or you need the row 1. If you need the row 1, you can do row 1. See how many rows? 100 rows. See, this for the first row. See, this way, row wise. See, this way. First person who gonna appear in the sample. First person, see, average from each and every sample from the 1,000 sample being calculated. See, average age of the second person, see, average being calculated. If you want, you can do that one. See, those are these numbers: 97, 98, 99, 100. Here, 1,000, see, x 1,000. The column has been labeled as x 1,000. First column has been labeled as x1, x1 through x 1,000. See? Now what are you going to do? I'm going to pick up sample. I can do this on different way. I'm going to go to data and say I need the first column. See, look at, I need the first column only. See, I'm going to call that one sample. See, 33, 32. Can you remember 33, 32? See, sorry, 33, 32. Is that the first one? 30, 33, 32, 30, 29. See, 32, 32, 30, 29. See, first column, if you can extract, see, bracket. This is for the row. You consider all the rows. That's why I say you need the row, but first column. Or you can say, call that one by that its label, x1. Another way to have a look at it. See, same thing. Or just simply go to data and then ask that give me the x1. See, it's the same thing. Okay, I'm talking about same thing. See, they tell us to do what in first question, what they want us to do. Let me get rid of this one. Okay. One sample, see, plot a histogram of age for the first sample, the first column of 100 students with the vertical line of the mean. See, with the vertical line of the mean too, you're going to plot a histogram of the age for the first sample with the vertical line of the mean. But first sample, that's the one that I extracted. See, I extracted. If I use the hist, see, like that. If you want to go to the line, see, AB line, you have to say AB line, vertical, the mean of the one sample, I'm utilizing one of them. I'm utilizing this one. Okay, one sample, one sample two, the same thing. See? So the line, mean of the sample is, you want a numerical value, 31.1. Or you can use the GF histogram that's setting. The GF histogram, see, one sample, fill blue, color, gray, and then you see, link to what? Vertical line, x-intercept. X-intercept is the mean of the one sample, color red, and the labels, see, pretty much everything we utilize in here. Oops. Here, I think I took this one. Just install the package. Okay, and this one. You see? Same thing. Oh, x-intercept mean one sample. Why, that's the same thing. This is, oh, x1. If you want, you can call that one x1 rather than call the one sample. You simply call the x1. See, x1, one shot. See? Still they do the same thing. You don't have to extract. You can extract too, but see, so many ways you can get this done. Simply you call to the data set, give the data set name, go to the data and extract x1. See, another way to do it. Shape of the histogram. See, you saw the shape of histogram very clearly from this one. You can see. See, skew to the right. So they're gonna ask some questions. Describe the shape of the distribution. What does the y-axis represent? Y-axis as what? Frequency of student, number of student. No. What do you mean by number of students in each bin? No. Each bin or rectangle. See, y-axis. How about the x-axis? What's the mean age for the sample? Part D, mean age. Mean age. See, I'm going to call that one the x1 bar. X1 bar. It's a superscript. See, x1 bar. X1 bar. X1 bar. See, x1 bar. X1 bar. The bar of this one. See, x1 bar. See, x1 bar. Bar on the top. So I can write this one. If you want, you can, to indicate that if you want, you can put a caret like this. Anyway, you, it doesn't matter. Anyway, you can write any way you want, but if you want to say that it's on the bar, but simply you call x bar, x1 bar. Okay. So x1 bar is 31.1. Then standard deviation of that one I call sx1. See, no bar this time. S subscript. See, for the subscript I use this one, underscore. For the superscript, if you want, you can put the caret. See, it's not actually superscript 2 that is on the bar. That's why I didn't even use the caret for that one. So this one, S of x1. See, so I'll see this one and its standard deviation. See, so this is what I'm talking about. See, I'm talking about this one. See, x1 bar. See? X1 bar is how much? 31.1. 31.1. See, that's the one I call x1 bar. 31.1. See, so, see. Number 2 RDC x1 bar. So this one I would say S of x1. See, S subscript. See, S sub S, I put like that, x1. See, that's the one. Which is see, S subscript underscore x1. See, 4.14. Like that. That's the notation. We get used to the notation. See? Because of the sample, we can tell like that. Okay. So the part for the part F, we're gonna ask that which notation. Okay. What is the standard deviation of this E? This part is E. Okay. So what is the standard deviation of the area? What notation would you use to describe the mean and standard error? Standard error, okay? Standard error, see? The notation that I would use to describe the mean and standard error, x1 bar and sx1 bar, because we are using only one sample. There's no error, okay? But simply the same thing you can utilize, okay? You can utilize the same notation I utilize here. Because we are dealing with only one sample. There's no error, but we call the standard error, see? Mean and standard error. Standard error is nothing but the standard deviation, see? Standard deviation of x1. Okay. Mean, see, mean of x1 and standard error means a standard deviation, see, of x1 actually. See. I'm gonna utilize the same notation I utilize here. Okay. Then part 2. In 2, but they will calculate the mean ages for each sample. Each sample, okay. I'm gonna use the function apply. They say use the apply function. You will need to figure out what values to put for the 3 arguments. There are 3 arguments inside. Argument means within the parentheses, we're going to call the argument. You put x, you put margin, you put the function. Let's say what these 3 would be. Okay. So see, there are several types of apply. Okay. I have mentioned over here. I'm going to give it. See, function, apply, L apply, S apply, T apply. S apply, if you use the apply, you put x, margin and function. That's the argument. If you use the L apply, you have x and function. If you use the S apply, you have x and function. T apply, x, comma, index and function. This one, apply a function to the rows or columns of both. See, this one there. Data framework or matrix. See, output vector, list, array, anything. Okay. It may be a vector, it may be a list or array. See, for different ways. Let's see that how to apply this one. Okay, in our discussion. Okay. I'm going to apply x means my data name. That margin is 2. 2 means produce output for column entries for the margin 2. If you put the margin 2, we're going to do column wise. Excuse me. That calculating averages this way, okay? This way. The same thing that I used earlier, what? Column means. Col means, that's the same thing. Col means. See? See, this way. Column wise, okay? If you put for the margin 1, row wise, okay? So sample means apply X data margin to function would be I'm interested in what? Mean. Produce output for column entries, this one. If you use the lapply, you give the data and give the function. Sapply, see, produce a vector of matrix output instead of a list for column entry. Let's see that how they look like. Okay, let's look at this one. Okay, then I get the head of sample means. Okay, how many sample means we have? 1000 sample means. 1000. Okay, can you remember? X1 has its mean. I'm talking about this one. Okay, here at the end of the day, here see mean. That means you have done that one column wise with the aid of that margin equals 2, and with the aid of this apply function. Then it looks like that. Let's use the L apply. Produce a list. See, list. L apply. I'm gonna use the list and see. And get the head. See, it is like a list. See, shows that way. It's not like a column. See, it's not like this way. See, like a list. It's being listed. The other one produces a vector matrix output instead of a list for columns. See? Again, it's very similar to that same thing that we saw in tapply. Sorry, apply. Okay. Tapply, you have to get a subset, okay, out of that one. If it is a subset, you're going to use the tapply. See? See, tapply, see, quantitative variable, see? Index quantitative variables or variables. Some variables index. See? But we don't have to worry about that one. Even over here, you don't have to use the 3 of method. You can use the 1 method, apply only, but I'm showing you more methods to get this done. Okay. When apply is applied for only 2 variables. See, look at the 2 variables. If you want to do the 2 variable, how to do this one? That's for the whole thing. This for the whole thing, okay? The whole data set, all the variables. It has been applied for all the variables. Here. See, all the variables. I'm talking about x1, x2, x3, all the way up to x1000. But if you want to apply to particular that 2 of them, see, you've got to apply this one like that. See, x1 and x2 particularly. But that's not what we are expecting. We want to do the first one the way that we did earlier. Okay. See, or you can use the sample means. You can use the sample means. That would give you the call means will give you the same thing. Okay. I'm talking about related to this one. Okay. Either these 3 methods or this method. This is subset of this one if you're interested in, instead of the whole thing. If you're interested in only certain number of variables, you can do like that. See, you set up like this. Margin is 2. If you put 1, they're going to do row wise. Okay. Your average would be row wise. Okay. Row wise. See, row sample means, I call that one row sample means. See, I just commented out so that we don't need that one. See, get like that. Or row sample you can get by the row means as well. See, either this method or apply method. Now what I'm gonna do, I'm gonna just get the pretty much everything using this some kind of a moments. I think we discussed this one at a certain point too. I'm gonna install these moments and then I'm gonna get the pretty much everything at the same time, because I need the mean and standard deviation both. If you need the mean and standard deviation both, how could we gonna do that one? See, I'm gonna go to the apply x data margin 2. I'm gonna build up a function. You're gonna go to the mean only at the beginning. Okay, mean is mean equals mean of x, whatever the value you put over here. See, x means data, bring it over here, and you put inside. See, another way to get this done. Same thing. See, then using the L apply, pretty much that setting. Get that. See, with the aid of that moments, you do that one. Now you really need the standard deviation. I'm going to do the standard deviation in the same format. See, the standard deviation. Another way to get this now. See, same standard deviation. See, like that. Now what I'm going to do? I'm going to get both at the same time. Tackle both. Mean and standard deviation both tackle at the same time. See, put the function C mean equals mean of x, comma, standard deviation is standard deviation of x, close, close. Okay, so for the C you close here, for apply you close here, for this one you close here. See, both you can tackle. See, that will show you both. See, mean and standard deviation, but it's not clear. See, it's a big mess. Okay, let's try this one using lapply. See, it's clear. I'm getting the first 6. See, mean and standard deviation clearly you can see. Then let's go to the lapply and see. And both will tackle. I'm sorry. See, again messy. So this one shows you clearly. See, all the columns, all the samples, means and standard deviations. See, this one we mentioned about that. If you know the kurtosis, skewness, you can tackle those two if you want, but you don't have to worry about this one. I'm just showing you for the sake of just for you to build up the knowledge. Kurtosis means the peakedness, skewness means the lopsidedness, variation means this is the center. Okay, this is in a distribution, this is the center, this is the spread, this is the variation, this is the peakedness, this is the skewness. You see all these properties when you have a distribution. You see all these. See, look at the peakedness means how peaked or flat. Some distribution are symmetric but flat. Some are see like this, peakedness, and it's been lopsided towards the center. That's called skewness. In addition to that one, we have a center, we have a spread, we have a variation. All the properties of the distribution you can tackle at the same time too. See, if you want to, but you don't have to. Okay, but in our the homework we don't have to. Okay, with the aid of lapply, can I do that one? See, clearly it's gonna show. So for the first sample, mean is 31, standard deviation 4, variance is 17, kurtosis is 2.88, skewness is this one. This is in another way. This the center. This is the second moment, third moment, fourth moment. In another way, another names like in physics they give the same name. That's why we call the moment. That's why we are using the moments package. Okay. But for our discussion, you need the standard deviation and this mean only. If you're not comfortable with doing in this way, it doesn't matter. You better learn. Okay, more the functions and then get things done in different ways. But you can do separately. Just to simply use the apply only. I'm talking about several ways to get this one. Apply, lapply, sapply. In addition to that one, mean and standard deviation, you can do at the same time. So many things. With the one line, you can get things done. Okay. And so many ways to get this done. Anyhow, and the question number 1 is whatever you got that one, I'm going to go ahead and use the call means for my convenience. It's not the only way to get this one. I'm going to call that one sample means. The column means I'm going to call that one sample mean. I'm not simulating, so I cannot use the sim SDOM. I'm not going to use that one. I can use later that one. See, I'm going to use later that one. If you want, I can use that one later. See, that's the same thing. See, sample means, or sample means go and get to the apply. Okay, function, same thing that I discussed earlier. Okay, same this thing being now we talking about same thing. As a data frame, you can call the sampling distribution of mean. You don't have to say simulated or not because we didn't simulate. It's already simulated. So therefore, you don't. It's already bootstrap. You don't have to worry about it. It's already built up. See, It's already built up. You simply call STOM enough. Whether that's a sim one or boot one, doesn't matter. Simply, they were already generated. They were already generated. Either through the simulation process or bootstrapping process. Doesn't matter. That's why I call STM. If you want, you can call that one. And then say get the head of those ones. You can check head of STOM. See, you can check. See, then you go to the histogram of the sample means. See, AB line. And mean of that one is nothing but 31.44. Standard deviation is mean of sample means. Okay, see, look at here. I'm gonna get the average of all the means. Now I have only one mean, see, which is 31.44. Earlier I have, see, 31.10, 32.61, 31.98, 34.47, and so on for 1,000 of them. They were being added together and divided by 1,000 to create this one, the mean of the sample mean. And the standard deviation of that one is 1.25. The sample deviation, 1.25. See? So earlier, standard deviation. The standard deviation of standard deviations. See? This would be what? See? It's the standard deviation of all the sample means. Sample means, go to the means. That's the spread of that one. Go to the mean and then find the spread of that one. See, I'm talking about, see, spread. This spread. You find its mean. Means the mean of mean. The mean of mean, which is the center. Mean of sample means. Average of sample mean is how much here? 31.44. 31.44. You can remember in the first sample, it should be 31.10. Now I get I'm not talking about standard deviation. I'm talking about the spread of the sample means. I'm talking about this guy. I'm talking about this one, this spread. In this particular distribution, this spread is nothing but, see, population standard deviation divided by the n. N, we know for sure, size of the sample is 100. But do we know the population standard deviation? No. Do we know the sample standard deviation? We have not only one sample, we have 1,000 sample. Now we have a question, which sample mean standard deviation would be utilized over here to get this done and check. Okay, let's go ahead and I'm gonna try something here. I'm gonna try something here. I need the standard deviation. Okay, this is 4.13. Let's say 4.13. Let's see. Look at it's easy. Okay, we don't have to even calculate in the 4.13. Okay, here I'm talking about here in the first sample, thinking that one of the samples is the one that I'm at or that in my hand. Observed one is this one. Okay, let's say observed one is this one. Okay, or if you want for this one, first one, 31.1, you can use as a mean. 1.5. See, 1.5, would that be similar to the center of the sampling distribution? Yes. It's not exactly the same thing. See, 31.15 here. Here we have a 31 point. See, 44. 44. We got this one by R. Can you by theory, this should be, this mean should be same as the one of the samples or the population mean. See, approximately 31 around that. And on the other hand, standard deviation should be, this standard deviation should be one of the sample standard deviation divided by square root of the n. This one is 4.26 divided by square root of 100, which is 10, which means 0.4242. See, it's far away from that one. See, doesn't match, because it doesn't match for a reason, because because we don't have a one of these we have many that sample in our hand. We don't know which one to pick. See, we don't know which one to pick. See, we don't know which one to pick. See, doesn't work that way. See, this one 1.25. If you get this spread, I'm talking about this spread. This spread should be same as the sample in your hand, standard deviation divided by the sample size. See, here, how many samples we have? Not only one in our hand, 1,000 samples. It doesn't work that way here because of that reason. Let's say that you have only one sample, then it's gonna work. Okay, let's see that it's okay. Okay, we can have overcome this difficulty later. Okay, so what I'm trying to say that see here, yeah, mean. See, mean, we found that one. See, sample mean. See, we draw the histogram, and then we put the line. We find the standard deviation. See, standard deviation of the spread. The standard deviation means the spread of this distribution is nothing but 1.25. Okay, so or you can get it done this way. Doesn't matter. From the central limit theorem, it's becoming what? Sampling distribution is regardless of your population distribution, regardless of population distribution. If you are dealing with symmetric or non-symmetric, if you are dealing with the large sample, your sampling distribution looks like a normal distribution. That's what the central limit theorem says. So this is very consistent with the, see, it complies with the central limit theorem. See, see, regardless of being symmetric or asymmetric, doesn't matter. If you are using a large sample, which is greater than 30, in our case it's 100, your sampling distribution is bell-shaped. How do you get the center? Center you get all the time, that very similar to the total population mean, as well as the standard deviation of the sampling distribution would be population standard deviation divided by the square root in sample size. See, that's why it's bell-shaped. Okay. Shape of the distribution. The shape of the distribution is symmetric and therefore appears to be normal distribution. Y-axis represents the frequency of means from the 1,000 samples. See? Mean of the sampling distribution of means. See? Mean of the sampling distribution of mean is the mean of sample mean. See? I'm going to denote that one by what? Mu sub x bar. Mu sub x bar. Mu sub x bar. Now they ask what kind of a notation. See, part D. Part D, what's the part D? Part D, question number 2. What's the mean of the sampling distribution of means? Part D. See, what is the standard error of the mean? See, standard error. Standard error. Standard error is the error of the sampling distribution of mean is same as the standard deviation of the sample means, or the standard deviation of the sampling distribution of the sample mean. In a bottom line, that there's sample. These two. The bottom line you are looking for. So this one. See, this distribution mean and this one. See, mu sub y bar. See, mu sub y bar. Sigma sub y bar notation. See, so I can say mean of sample means. See? All the means, there are 1,000 means. Their average, and they've been already put into a histogram. See, like this. And now we need the mean of that one. Its center. Its center. We really need its center. Its center is what? Center is the mean of all these means. Okay. Okay. So when you see, when you draw histogram, see, like this, if these are y bar, see, mean, sample means, see, sample means. So this one bell shape from the central limit theorem, see, bell shape. This one, see, mu sub y bar, center, the center they are looking for, mu sub y bar, see, mu sub y bar is mean of what? Sample means, according to, I call that one sample means, so sample means. Not. So that's how much. Mean of sample means sample means. I'm gonna get this one wrong and get potential 31.44. 31.4417 in the spread. I'm gonna say sigma y bar, sigma sub y bar, same as what SD of sample means, which is 1.2503. So that's the, standard error. The standard error means sigma sub x bar. See, mean. If you want to mean, now go to the favorite stat. See, favorite stat. See, you can go to the favorite stat of sample mean, would give you both of them. Or you can go to the mean and apply, and they see, look at you apply the mean average. You're gonna find the average of all the columns by using apply, and you're gonna find the mean of those values. It's the same thing. See? 31.44, 31 point. So many ways you can get the average. See? Favorite stat, or go to mean of sample mean, or favorite sample of sample mean, or go to this way. Standard deviation, same thing. Standard deviation, see? Or go to favorite stat, it's already there. Or get the SD of the apply and then get the SD of that one. Same. See, they're gonna ask which notation you use, mu sub x bar and sigma sub x bar. See? Mu sub x bar. See? So in a question number 3, that pretty much that you're gonna do the same thing. Now you change a little bit. Okay. Now what are you gonna do? Now you can say sample standard deviation. See. See, calculate the standard deviation this time, not the mean. I need the sample standard deviation. And that's why I'm going to, for the function, I use the SD. See? 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 And draw the histogram for the standard deviation. Okay? I'm going to little bit do this one and we can stop and then we can continue tomorrow. See? And if you draw the histogram for this, all the standard, see, this one, some standard deviation. How many standard deviation I'm talking about? 1,000 standard deviation, 1,000 columns. So if you draw the histogram for that one, see, okay, symmetry. The mean of the sample standard deviation is how much? 3.9. Or favorite stat, if you go mean and standard deviation, both can be tackled. See, 4.1, I'm sorry. I'm at the wrong place. See, 3.99 standard deviation is 0.27. Okay, this is what I'm talking about. This time, you have to be careful. I'm drawing this one. This one has a name. Sampling distribution of, okay, this one, this is sampling distribution of y bar. Y bar means sample means sampling distribution of y bar. Okay, sample means. Okay, this time in the number 3, you draw the histogram for S, okay? Sample standard deviation. Sample standard deviation. Then again, it's going to fit in into a what? Normal distribution, symmetric distribution like this. Again, here the frequency, how many going to fit in into like each bin, see? It is center, see? Look at center. Center is nothing but mu of S, see? See? Mu sub S. That center, how do you get that center? You go to mean, you're going to say sample standard deviation that you already generated. From that one, you get the see, center. This is spread of that particular distribution. This distribution name sampling distribution of sample standard deviation. How do you get the spread? Sigma of S. Sigma sub S. How do you get that one? SD of sample SD. Okay. I'm gonna get the SD for all the columns. Then find the histogram. Then find the mean of that guy, which is 3.99. I'm gonna put over here 3.99, almost 4. Okay, 9907. And the standard deviation 0.2764. See? That's what we're doing over here. Or you can do this way. The same thing. Shape this is symmetric. I represent the number of standard deviation from the 1000 sample. See? The same way you're gonna mean of sample deviation, mu sub S. Same thing. 3.99. And this one. Okay. This, that's the same thing. Number 3, we're gonna do that one. This can be done for like any estimator. That's what we are trying to do over here. B naught, can you do the same thing? Yes. Can you find the center? Yes. This center is same as, okay? This center, see, the mean of S standard deviations. The spread 0.2764. Okay. Then later on, they're gonna, according to your finding from Q1 through Q3, what is your best estimate of the population mean? The best estimate is not a mean of one sample. No, not a mean of 1,000 samples. That's the average of all the samples. No. Okay. So see, best mean is nothing but the mu sub y bar. Can remember the average of averages. That's the best mean. But the best standard deviation would be nothing but the mean of the sample SD, okay? Not the SD of SD. Mean of SD would be best SD. See? the center in any distribution will be the best. See, this would be the best estimate for this guy. That's what I'm trying to say. This would be the best estimate for, this would be the best estimate for whom? Population mean. See, this is the best estimate for whom? The population mean. This is the best estimate for what? The population standard deviation. You cannot pick any of these. Instead of picking any of these, spread we're going to take into account, and then you can go to the center all the time. See, you can say best, see, best estimate for the population standard deviation is what? That means this one. Sigma hat is nothing but mu of S, which is 3.9907. A similar way, I can say best estimate for the best estimate for the. I can write here. Okay, I'm gonna write here. Best estimate for the population mean I'm gonna take a change here. Okay, a little bit change here. The standard deviation, which is sigma, is okay. The population mean, which is mu, is what? Mu hat is nothing but mu of y bar. See, which is 31.4417. So the rest, I think you can keep doing that one, and then we can build up this discussion, and then we have plenty of time. Tomorrow we can finish this one. Okay. So do you guys have any questions? Anything? If not, I'm gonna let you go. That you guys have a good night. See you tomorrow, and then take care, and then stay safe and be well. Okay. See you tomorrow. Good night. Take care. Thank you. Thank you very much. Yeah. Thank you very much. See you tomorrow. Take care. Thank you. Take care. See you tomorrow. Take care. Thank you.